So the first order of business is going to be then to figure out what the graph of sine and cosine looks like. So when we talk about transforming it, we know what it is that we're talking about, right? Does that feel okay? All right. So let's start with sine x. So if I'm graphing sine x, the x coordinates are going to be an angle measure, right? What do we plug into sine? Angle measures. Everybody okay with that? And what comes out is going to be the y coordinate from the unit circle at that angle measure. Everybody's cool with how that kind of works? So, okay, if we're going to graph something, do you think we're going to prefer to use angle measures in degrees or angle measures in radians? Well, if I have to do the full unit circle, how many degrees are we talking about? 360. If I do the whole unit circle in radians, how many radians are we talking about? 2 pi. So if I'm going to graph something, would I rather put 360 tick marks on my x-axis or like 6 and change? 2 pi is like 6.2 something or another, right? That sounds a lot nicer to me. You guys agree? So when we're graphing, typically we're going to use radians to do that. So what I'm going to do now is I'm going to use the unit circle to generate points for the sine function. I'm going to plot those points using this graphing software right here. We're going to look at the pattern that we get. Everybody cool? So the first angle measure I'm going to use is 0 radians, and sine of 0 is equal to 0. So I'm going to plot the point 0, 0. The next angle is pi over 6, and the value for sine of pi over 6 is 1/2. So I'm going to plot the point pi over 6, 1/2. And we're going to do pi over 4, root 2 over 2. I'm going to just use the decimal approximation for root 2 over 2, which is 0.707. The next angle is pi over 3, and then the output is square root 3 over 2. Again, I'm going to use the decimal approximation of that, which is 0.866. And then we have the next angle is pi over 2, and the output there is 1. And I'm just going to kind of continue doing this. So I'm going to stop highlighting things. Is everybody okay with that? Hopefully by now you kind of get the pattern of what I'm doing here. Notice on the picture here the points that are being plotted. So that's happening in real time for us. Yay, real time. Oops. Yuck. That's what I get for just looking at my keyboard and not looking at where I'm at. Okay, so there's the full unit circle around. Everybody cool with what we're looking at here? Oh, let's do this real quick. There. Now the x-axis is in terms of pi's. That probably helps. Everybody see what we're looking at? So this shape here is the shape for the sine function. What would happen if I went around the unit circle again? It would just continue, right? So I'm going to be getting the same shape over and over and over in both directions. Everybody's okay with that? Okay. So drop these in here real quick. Oops. So this guy was the graph for sine x. Oh, I didn't want to do that yet. You go away. You come back. So if I were to graph just sine x, you see in red here, that's the graph of the sine function. See, it follows the points that we plotted exactly. It keeps going with that same pattern in both directions. That's the picture I wanted to take. What if we do the same thing now for cosine? What's going to be different here if I'm graphing the cosine function? Well, the input is still going to be an angle measure, but the output's going to be the x-coordinate from the unit circle. Everybody's okay with that? So I'm just going to update my picture here using the x-coordinates. Oops. Ah, shoot. Boogers. Typos are the worst, guys. You know? Here we go. It's third quadrant. So that's the graph of cosine from the unit circle. And if I wanted to extend that in either direction, the graph is just going to repeat. So if we take a look at this, if you look at the shape of these sine and cosine graphs, what do you notice? Well, they both have the same general shape, right? They both have this wavy kind of shape. Everybody agree with that? That kind of, a graph that has that kind of wavy shape is called a sinusoid. And notice how that the part that we graphed with the points just repeats over and over and over again. Everybody see that? A graph that repeats over and over and over again is called periodic. And then if you look at the two functions here, the sine and cosine function, if I say I took the cosine function and I shifted it like to the right a little bit, what would I end up having? So like if I take that, everything on the cosine function, I shift it to the right a little bit, what's it going to look like? Exactly the sine function. Or I could have taken the stuff on the cosine function and shifted it back a little bit more, and what are we going to end up with? Just the sine function again, right? Like you could shift cosine left or right, different amounts, but you can end up with sine again, right? And you could do the same thing with sine. You could shift it left or right and end up with cosine. Everybody's okay with that? All right. So that observation will be important kind of tomorrow, but I want to point that out today, that the shape of the sine and cosine functions are identical. They're just the same thing. They're just shifted a little bit, either left or to the right. Everybody's okay with that? So let's talk about transformations now. So recall from last time that if I have some parent function f of x, the resultant function or transformation of that function can be thought of as a times f of 1 over c x minus h plus k. Today we're going to talk about specifically when f of x is equal to sine x. So my resultant function would be g of x equals a times sine of 1 over c x minus h plus k. And also where my parent function is cosine. So in that case, the resultant function would be g of x equals a times cosine 1 over c x minus h plus k. So let's look at a couple of examples. Something weird is going on out there. So let's say we have the function y equals negative 4 sine of 2x plus 1. And our directions are going to be to describe the transformation. So this is essentially an identical problem to what we did last time, right? Our first order of business is going to be to identify the values for a, c, h, and k. We'll do that the same way we did last time by taking our current function and trying to write it in that general form. So I'll start with y equals negative 4 times sine of, and then here's the tricky part. Somehow I have to rewrite 2x as 1 over c times x minus h. You guys remember how we would do that? Anybody want to volunteer a try at that? Great. So we'd have 1 over 1/2. And then what is the h in this case? So notice that there's nothing being added or subtracted in here. So what does that mean h must have been? Not 1, because we're adding and subtracting. 0, right? X minus 0 is still x. And then x times 1 over a half is just 2x, right? And then we have the plus 1 at the end. So we have a is -4, c is 1/2, h is 0, and k is 1. Just like last time. And then just like last time, we're going to use our set of criteria. Of course. To describe the transformation. So since the c is positive, we have no reflection on the y-axis. And since the magnitude of c is less than 1, we have a horizontal shrink by a factor of 1/2. Since the a is negative, we are going to have a reflection on the x-axis. And since the magnitude of a is bigger than 1, we'll have a vertical stretch by a factor of 4. Since the h is 0, we'd have no horizontal shift. And since the k is positive, we're going to be moving up 1 unit. So there's my description. Yes.
So I know you talked about this yesterday, but I'm just confused about the 1 over c. So is it always 1 over 1/2, or does it depend on the number that's with the x?
So it depends on the number that's the coefficient on the x. So here, 2 must be 1 over c. So that would mean that c is 1/2, right? Like if 2 equals 1 over c, 1/2 should just equal c. So when I write this as 1 over c, I write it as 1 over 1/2. Just because we took the reciprocal of both sides.
Oh,
yes.
Okay.
Does that feel okay?
Yeah.
Sure. And again, if you're confused at something like that, that's just like how I'm rearranging things, feel free, stop, ask. We'll say it again, try to clarify. It's important you understand, right? It's usually never that complicated, but sometimes you're just like, oh yeah, okay, I just missed it. Got it. Cool. Should we do another? Why not, right? Okay. So let's say we have negative sine of negative x over 2 minus 3 all minus 5. So just like before, what am I doing here? Being really tired and making mistakes. That's what you're doing, Mr. Kulek. Okay. Yes?
I need to react to the address.
Okay. So again, first step would be to write this in our general form. That's the general form. All right, let's start kind of cracking away at this. So we have y equals. Now I have a negative sign out front. How do I write that as a? Negative 1 times, yeah, that's right. Okay, now the tricky part, I have to take this and write it as 1 over c times x minus h. So I would do this in 2 steps. Everybody okay with that? I would start by trying to factor so that the leading coefficient on my x is 1. Right now, what is the leading coefficient on the x? Negative 1/2. Is everybody okay with the negative, why it's negative and why it's 1/2? Because x over 2 is the same as 1/2 times x, right? Okay. So let's factor that negative 1/2 out. Okay. When I take negative x over 2 and divide it by negative 1/2, I just get positive x. Good with that? When I take negative 3 and divide it by negative 1/2, I'm going to get positive. And what's 3 divided by 1/2? Nope. What's 3 divided by 1/2? Go back to elementary school. You do this by multiplying by the reciprocal. Everybody's okay with that? But we still have one small problem. That's got a negative sign there. We have a plus sign there. What do I do to fix that? Plus is the same thing as minus a negative. Yeah. Is that okay with everybody? So my a is negative 1, my c is negative 2, my h is negative 6, and my k is negative 5. Does that all feel okay? All right. Since the c is negative, we have a reflection across the y-axis. And since the magnitude of c is bigger than 1, we have a horizontal stretch by a factor of 2. Since the a is negative, we're going to have a reflection on the x-axis. And since the magnitude of a is just 1, we're going to have no vertical dilation. Since h is negative, we're going to be going left, and then 6 units. And since k is negative, we're going to be going down, and then 5 units.
Mr. Kulik?
Yes.
I have a quick question.
Sure. What's up?
Why would this c be negative? If a negative over a negative half, isn't that just a positive? So how do you determine, like, oh, it's the 2 that is the negative?
Okay. Because my equation needs to be 1 over c. So I know the numerator has to be 1. So the negative had to go into the denominator.
Okay, thank you.
Fair question. No problem. Ava.
I'm just still confused about the negative 1/2 being 1 over c from like the original. Because wasn't it x, negative x over 2? So I'm just confused again.
So negative x over 2 is the same thing as negative 1/2 times x, right?
But we don't know what the x equals.
Yep, that's fine. Right, because I could just put a 1 there, right? Still okay? So it just still could be 1x. And when we multiply fractions, we just multiply the tops together and the bottoms together. So I can write that x over 2 is just 1/2 x. Is that okay? That's what you needed?
Yeah.
Okay. All right. We feel okay doing this process? Not really any different than last time, right? It's the same exact process. The only thing different is f is now sine or cosine. Whoop-de-doo-doo. Doesn't really change anything. Let's talk about graphing then. That was the other thing we had talked about last time. So when we graphed, what we did is we took some points from the parent function and we transformed them into points in the resultant function by using this map. The question becomes, what points from the parent function do I want to use? Well, if you remember at the beginning of the lesson, we generated a bunch of points on the sine and cosine functions, right? Look at all the points we just generated here. Oh, Mr. Gulick, I have to transform all of those? That's like a lot of them. We're not going to use all of them. We're going to use those ones for sine. And these ones for cosine. Just 5 of them. We'll leave those other 12 alone. What's significant about the 5 points I've chosen in both sine and cosine? They are either x-intercepts or the extremas, right? The maxes and mins. Those are the key points. That's all I really need to get a decent picture is where it's crossing the x-axis and what are the high and low points. Everybody cool with that? Now, you're going to say, Mr. Kulik, what are the coordinates for those points? Like, do I have to memorize those? Well, nah, dude. I put them all into this sheet right here that has the key points or the reference points for sine and cosine that I've collected here. Would you have to memorize these? No, I'll give those to you on the test. Or you could put them on your note card if you wanted. That's fine. Either one is okay. I'll give them to you, though. You don't have to waste your time recording those. Okay. All right. Well, that's easy enough then. Like I have the key points. Let's do an example then, right? All right. Let's say we have y equals 2 sine of 2x plus 3 pi over 4 minus 1. Everybody's okay with that? Just like before, my first order of business is going to be to try to write this in that general form so I can pull my values for sine or for a, c, h, and k. So first thing I'm going to do is I look in here. I notice that the leading coefficient on x is not 1 already. So I'm going to start by factoring off a 2. Ooh, guys, I'm going to change this problem just a little bit. I'm going to make that a 4. Sorry. Or change that 4 to a 2. So let's start by factoring a 2 out. So when I factor the 2 off, the 2x becomes x. And then what does 3 pi over 2 become? So dividing fractions is the same as multiplying by the reciprocal. So it should be 3 pi over 4. Is that okay with everybody? And then what's the issue still? It needs to be minus h. I've written minus plus h. How do I fix that? Oh, well, there's 2. There's another thing also going on, right? I need to write as 1 over c. I've written it as just one thing. So how do I write 2 as 1 over c? We use the same trick we used before. 1 over 1/2. And then how do I write a plus as a minus? Minus a negative. So those are my values for A, C, H, and K. Once I have that, I can write my transformation map. So when I plug things in, I'm going to have 1/2 x minus 3 pi over 4, 2y minus 1. Okay. I'll go to my reference points, and because I was graphing a sine function, I'm going to grab the points there in yellow. Now, Mr. Kulik has these memorized because he's a crusty old math teacher that's been doing this for like a million years. You guys would just, look up what's given to you. Everybody's okay? So now to transform this, I'm just going to be plugging the x coordinate into the spot for the x's and the y coordinate into the spot for the y's. 1/2 times 0 is 0. 0 minus negative or minus 3 pi over 4 is negative 3 pi over 4. 2 times 0 is 0. 0 minus 1 is negative 1. And I'm just going to kind of keep doing that. One-half times pi over 2 is pi over 4. 1 pi over 4 minus 3 pi over 4 gives you negative 2 pi over 4. I'll write it that way, even though that's the same as negative 1/2 pi. And then 2 times 1 is 2, minus 1 is 1. Just kind of keep on going. One-half times pi is pi over 2. That's the same thing as 2 pi over 4. 2 pi over 4 minus 3 pi over 4 gives me negative pi over 4. 2 times 0 is 0. 0 minus 1 is negative 1. One half times 3 pi over 2 is 3 pi over 4. Minus 3 pi over 4 is 0. 2 times negative 1 is negative 2. Minus 1 is negative 3. So 1 half times 2 pi is 1 pi. 1 pi minus 3/4 pi is 1/4 pi. 2 times 0 minus 1 is negative 1. So what I'll be plotting then are these 5 points. Just go grab some graph paper here. Okay, so let's see. I have to graph things by quarters, right? So between 0 and a half, halfway in between there must be a quarter. So I know I'm going to need every quarter, so I'll just mark those. So every tick mark is basically a quarter pi. So negative 3/4 pi, comma, negative 1 would be like there. Negative 2/4 pi, positive 1 would be like here. 1/4 pi and negative 1/4 pi and negative 1 would be here. 0, negative 3 would be down there. And then 1/4 pi, negative 1 would be there. So there's what I've plotted. But Mr. Kulik's going to ask you to extend your graph so that it covers the space provided. Now I'm not going to generate more points to do that. I'm just going to kind of use my eyes and follow the pattern. So after the midline, we went up to a maximum, and then back to the middle, down to the minimum, back to the middle, up to the maximum, down to the middle, down to a minimum, back to the middle, up to a maximum. So I'll just do this in dash to show you guys that I didn't actually, this is not coming from the stuff that I generated, it's just me extending what I did. And I'd extend in the other direction also. So I'd go to the minimum, back to the middle, up to the max, back to the middle, down to the minimum, back to the middle, up to a max. Just kind of following that same pattern. And that's the gist of it. Is this really any different than what we did last time? Not really, right? Oh, what a relief. It's the same thing. It's just different points? Yeah, but so what? Just different points. That's not a big deal. I do have one little piece of vocabulary that I meant to do earlier that I forgot to do. Can we go back and do that? My apologies. I just got excited and got going too fast. Okay, so when we look at these graphs of sinusoids, there's four pieces of vocabulary that are going to be important here that describe characteristics of these sinusoids, these wave graphs. So the first one is the midline. And we're just going to kind of draw what they look like on the picture, then give the definitions in words. The midline is a horizontal line that divides the graph in half. So if I'm looking at this graph of sine, my midline is right here on the x-axis. Notice that there's the same amount of graph that's above the midline as there is below the midline, right? Everybody can kind of see that? The next piece that we're going to talk about is the amplitude. The amplitude is the distance from a extrema to the midline. So like any of these guys would be considered amplitudes. What's the amplitude here that we're seeing? It's 1, right? If I trace this point over, it looks like it's at y equals 1. Everybody's cool? It doesn't matter where whether you use a maximum or minimum, it doesn't really matter. Okay. The next piece is the period. The period is the length of the longest non-repeating segment, like the horizontal length. So let's say we start here. If I do that much, that is 1 period. Okay. How far horizontally did we travel? If we started at 0 and we end at 2 pi, we went 2 pi. Is that okay? All right. And the frequency then is a rate. It's the number of periods per 1 unit of the graph, or the number of periods accomplished in 1 unit of the graph. So this spot right here is pi. Pi is like 3.1. So after 1 unit would be, I don't know, like right about here would be like 1 unit, right? Everybody feel like that's a reasonable estimate?
So it's, how would you define it?
Like 1 over, like on the x.
Oh.
Like we're just going 1 over on the x. That's what I mean by a unit. So we're talking about this much of the graph, right? How much of a period happened in one of those? It's probably about a 1/6, right? That seems like a reasonable estimate. If I keep ticking over that much of the graph, about 6 of those will cover the whole thing. Well, it turns out the frequency is just going to be 1 over the period. Remember, the period in this case was 2 pi. Two pi is like 6.2-ish. So just about a 1/6, right? Oh, okay. So what about it kind of looks like? So that's like what we're talking about with the frequency. It's like how much of the graph gets done, how much of the period gets done in when you moved over 1 unit, inside of 1 unit length horizontally. It's all right? Just some little, we'll do some more with these midline amplitude, period, frequency next time. But I just wanted to get the vocab in today. All right, that's as much as I want to do today. I feel like that's a good mouthful of content for you guys. From the problem set, I'd like you guys to be able to do, let me just grab the values here. Uh, 9 through 12. And then worksheet 3. Yeah. Yes, sir. Of course. So that's what I'd like you to work on here for next time. Next time, we'll talk about how to find the values for midline, amplitude, period, frequency on a transformation. And we'll talk about how to go from the graph of a transformation to an equation. Ooh. And then the next day we'll go from information about the graph back to the equation. So you don't get the whole picture, you're just going to get like a little bit of information about it. So that'll be the next 2 days. That's all still in section 3.1. That's all still the first section. Everybody's okay?
Yeah.
All right.
No one's doing